All right, we're live. This time, for reasons I don't understand, we're much bigger. So hopefully that will help. And since we're much bigger, you can read my obligatory disclosure that I am an employee of Columbia University. Columbia University has received several research grants to develop STAN. I'm also a co-founder of the startup STAN Group, which provides all kinds of things for businesses using STAN. And according to Columbia University conflict of interest policy, any such employee is required to disclose these facts in any and all public presentations. So the goal for the class today is to continue to learn about continuous random variables and working with probability distributions and whatnot for those. The continuous case is going to be more confusing than the discrete case, which it seems like we understood pretty well with bowling. So make sure that you continue to ask good questions and provide good answers on Piazza for probability with continuous random variables or anything else related to the class. And also today we want to rederive the posterior distribution that Thomas Bayes originally figured out in like 1760 something ish. I can't remember the exact year. No one really realized he figured it out until after he died. Somewhere around there, long time ago. But that's when Bayesianism got started, sort of. It had to get restarted several decades later and then restarted again and again over the years. But we're going to do the one that Thomas Bayes did originally. So to just pick up where we left off last time, differences between the continuous case and the discrete case, particularly as it regards to this PDF. So a probability mass function tells you the probability that a discrete random variable happens with whatever probability. It's going to be some function. It's going to be a non-negative function, and that function is going to sum to 1 over the entire sample space. A probability density function does not yield a probability. It does not input a probability. It does not output a probability. Rather, the PDF is merely the slope of the CDF. CDF, cumulative density function, being the probability that a continuous random variable x is less than or equal to any particular value, little x, from the sample space of that random variable. So the PDF can be obtained by differentiating the CDF. It's the line tangent to the CDF. It's the rate of change in the CDF, but it is not a probability. So the CDF outputs a probability and the PDF outputs a slope. But because the PDF is the derivative of the CDF, in principle, and this actually often happens, you can start with the PDF and do an integral of that to obtain the CDF, the probability of it being less than or equal to. Consequently, while the probability mass function sums to 1 over the entire sample space, in the discrete case, a PDF, the integral of the PDF is 1 over the entire sample space for a continuous random variable. So these PDFs are special kinds of functions. They often have weird forms, but we say they're normalized because every PDF, the area under the curve is going to be equal to 1. So if you do the definite integral of a PDF with the limits being the lower bound and the upper bound of the sample space for that variable, that definite integral, that area will always be 1. So because the probability mass function yields a probability, it's going to be restricted between 0 and 1. Because a PDF is not a probability, but rather a slope of an increasing function, it will always be positive, but it can be greater than 1. It can even be infinite. But it will integrate to 1 over the entire sample space. So in the discrete case, we can sum the PMF to get the CMF, whereas in the continuous case, we would have to integrate the PDF to obtain the CDF. So conceptually, it's sort of easier to start with the CDF and differentiate it to get the PDF. But in point of fact, historically, people often start with a function, figure out what it integrates to, divide by that, and now you have a valid PDF. And that's mostly because doing integrals is much harder than doing derivatives. In fact, most integrals are actually impossible to do in any sort of a useful analytic form, whereas essentially any differentiable function, you can figure out what the derivative is and derive the PDF from the CDF. But all those differences aside, the PMF and the PDF are used in very similar ways, depending on whether you're talking about a continuous or a discrete random variable. So things that you can do with both the PDF and the PMF, the generalized multiplication rule holds. So you can multiply a marginal PDF by a conditional PDF and obtain a joint PDF, in this example here, of x and y conditional on some unknown parameter theta. If you can do the general multiplication rule, you can do Bayes' rule just by dividing and taking advantage of the fact that you can do the conditional either way. So we can reverse this around and get a PDF for theta, which is the unknown parameter that we're trying to make inferences about, conditional on the data y and x. And we can write that as a PDF for theta, which expresses our beliefs about theta in the form of a PDF before we see new data on x and y. We can multiply that by a conditional PDF for y given theta and x. Those two things together define a bivariate PDF for theta and y conditional on x. So that's the numerator of Bayes' law. And then the denominator of Bayes' law is the marginal PDF of y without irrespective of theta. And if we divide the numerator by the denominator, we get a new PDF, a conditional PDF for theta given y and x. And because it's a PDF, we know that f of theta given y and x is going to integrate to 1 over the sample space of theta. And so we can do all kinds of probability stuff on that conditional PDF. And this is exactly the PDF that we want. It describes the unknown theta conditional on the known data we have, x and y. Now, the denominator of Bayes' rule is difficult to obtain, and here's why. When we did the bowling example, and I said, okay, how do you get the denominator? How did we do that? The marginal probability of knocking down x2 pins on the second roll? Sum down the columns. That works in that case because there was only like 121 things that could happen, and most of which were impossible. There was a discrete states, like a pin can be up or down. It can't be like tilted a little bit. It doesn't work that way. And there's a finite number of them. The analogous thing, if we're talking about a continuous sample space, such as theta, we can't sum down the columns of like theta because theta is a continuous thing in the way I've written it down here. To do the analogous thing, we have to take the integral of the numerator over theta space. So we multiply the marginal PDF for theta by the conditional PDF for y given theta. We now have a joint distribution of theta, a joint PDF of theta and y. And we want to take that function, do the integral of that over theta, over the sample space of theta. That's going to be a new function. And because we've plugged in that definite integral, like the upper limit of the sample space of theta and the lower limit of the sample space of theta, when we do that definite integral, we're going to get a new function that only depends on y. So in the discrete case, we can sum points. In the continuous case, we have to integrate over area. And doing that integral is a lot harder than just doing a summation. But assuming it can be done, and you can always do it in principle, but we sort of lack the mathematical tools to do it in practice a lot of the times, and so we have to find a workaround for that. Anyway, if you can obtain the denominator, you can divide, and now you have this conditional PDF. Also, it's always the case that 1 minus the CDF yields the probability a random variable big X is greater than some value from the sample space little x. So are there any questions about the similarities and the differences between continuous and discrete random variables, especially their PDFs, before we go on? Yes, Adam.
Not a question about the differences, but so this integration and denominator, that's what makes using Bayes' rule of practice computationally expensive?
Well, what makes it analytically impossible, because there's very few integrals that we can actually solve with a pencil and paper. So you either have to do some numerical integration stuff, or the other thing is if theta is a vector, this is actually a multi-dimensional integral. So let's say you have 1,000 parameters. Now you're doing an integral, like 1,000 integrals. So yeah, this is hard and actually impossible most of the time. Yeah, so in order to do this in practice, we're going to have to learn a way in which we can get random draws from the posterior distribution using only the numerator. So the numerator can get ugly, but it's tractable. The denominator actually involves integration, and you can prove a lot of integrals can't be done in a useful way. So that's an obstacle. That was historically the biggest obstacle to using Bayesian inference. Do you have a question, Steve? No. You have a broken wrist? No. Okay. Yes.
I'm just a little confused about the form. I thought to get the marginal probability, you need to integrate the point probability in the variable that you want to get rid of, right?
Yes. So if you want to get rid of theta, you integrate over the sample space of theta. If you wanted to get rid of y, you would integrate over y. But in this case, to get the denominator, we want to purge theta and leave ourselves with a function of y only. Good questions. Yes, keep them coming. No more questions? All right. So by far the most important continuous distribution is the normal distribution, and we're going to start with a special case of that known as the standard normal distribution, which you may already be familiar with. What you are probably not familiar with is that the CDF of the standard normal distribution can be written in this form. CDFs are often a little bit ugly. So here we have 1/2 times this thing involving the square root of 2 pi, e, again, the number 2.7128. And then in the exponent there, we have negative z squared over 2. So z is the random variable in this case, and the CDF is a function of z. But then we have to multiply that thing by an infinite summation. This thing involves z to the 2i plus 1 in the numerator and the double factorial of 2i plus 1 in the denominator. You may not have seen the double factorial before, but it's like the factorial, except you go down in steps of 2. So like the double factorial of 5 is 5 times 3 times 1 instead of 5 times 4 times 3 times 2 times 1. Anyway, that's not essential. But this is the function that evaluates to the CDF for a standard normal random variable. So this is complicated, and it's implemented, or something equivalent to this is implemented in R by the p-norm function. So in R, there's a universal convention that CDFs start with the letter P, and then there's some suffix to it that pertains to the distribution, like norm. So because the CDF returns a probability, that's why it starts with P. The PDFs start with the letter D and then have the same suffix. So like D norm for density if you want the PDF. And so you can obtain the PDF by differentiating the CDF with respect to Z. And we're not actually going to go through the mechanics of that. It's, not that hard. There's just like a products rule that you got to do there, and then a bunch of simplification. It turns out to be The PDF is this middle term here, 1 over the square root of 2 pi times e raised to the power negative z squared over 2. That's not a universal thing that the CDF can be written in terms of the PDF. But if you differentiate this CDF, you get the following function for your PDF. And like I was saying, this is implemented by the denorm function in R. And if you've seen the standard normal distribution before, you've probably seen the formula for the PDF rather than the formula for the CDF. So this function here is the partial derivative with respect to z of that function there. But when it's taught at like the undergraduate level, you usually only see the PDF, and you're sort of, usually it's not really explained where the PDF comes from. It just comes from the textbook. So, questions? Everything you wanted to know about the standard normal distribution that you're afraid to ask? Yeah. How about a graph? It's a little hard to see. Well, the green is hard to see. Why did I use green? All right, so the black line here is the CDF. CDF is always a function from the sample space. In this case, the sample space is all real numbers. And the CDF, because it's a probability of being less than or equal to whatever is on the horizontal axis, is going to be bounded between 0 and 1. And this CDF, like a lot of CDFs, has this sort of elongated S-type shape because it has a lower bound of 0 and upper bound of 1. But at any point along this black line, we could draw a straight line tangent to it, and that straight line would have a slope, and the slope of that straight line is equal to the derivative of the CDF. And the derivative of the CDF is given here by the red dashed line, which is the PDF of the standard normal distribution. So if you've seen the standard normal distribution at all before, maybe you didn't even see the equation for the red line, but you probably saw the shape of the red line, which has this sort of bell curve shape to it. And you can imagine, you know, integrating the red curve from like negative infinity to 1, let's say. Here's 1. You could calculate how much area there is underneath the red curve between negative infinity and 1. And that number would be equal to the black curve evaluated at 1. Because the integral of the CDF, integral of the PDF is the CDF. What you probably have a hard time seeing is the green line, which we'll come back to later. But that function is equal to the PDF multiplied by x. And so when x is negative, the green line is negative, and when x is positive, the green line is positive. We'll come back to that. But everybody's seen the bell curve thing before? Probably? Okay. So we talked about expectations last week, last time something. No, Tuesday. How to do the expectation of a function of a discrete random variable. So now we want to generalize that, talk about the expectation of a function g of a continuous random variable big X. And the expectation of g of x is going to be defined as in terms of an integral. So the expectation with respect to x of the g of x function can be anything, is defined as the integral over the sample space of x of g of x multiplied by the PDF of x and integrated over x. And that PDF can be a conditional PDF, you know, if it involves some parameters theta or something like that. So in the discrete case, we did the summation of g of x times the PMF of x summed over all the elements in the sample space of x. When x is a continuous random variable, conceptually, we don't really do this in practice that much, but conceptually, it's the integral of g of x times the PDF of x integrated over the sample space of x. So this expectation of g of x is an area. It's the area under the curve g of x times f of x. But some of these expectations are important. Well, first of all, some of these integrals are impossible. So this is just sort of conceptually an area, and computers can approximate that pretty well if necessary. We just really need to we'll do like maybe one integral the whole semester for homework, but we need to understand what these integrals are conceptually. It's the amount of area under some curve. In this case, it's the curve defined by the product of g of x and f of x for any PDF involving x. So like in the discrete case, there's some g of x functions that are so important that their expectations have special names. So if g of x is equal to x, which is to say it's an identity function, then the expectation of x is, you know, the mean or the average conceptually has a special symbol, Greek lowercase letter mu. If we take the function g of x is equal to x minus mu quantity squared, the expectation of that function is the variance of x, and it has the special symbol sigma squared. We can take the square root of that. It's the standard deviation of x. So at least conceptually, we can define the expectation of any function of a continuous random variable x. If we can do that integral analytically, great. If you can look that integral up in Wikipedia or Wolfram Alpha, even better. And if it's impossible, then we'll do this integral numerically. But it's really just the area under a particular curve. Choose your g of x function that you're interested in, multiply it by the PDF for the random variable that's an input to that g function, you get an area. That's all there is to it. All right? Questions about that? So what's the expectation of, in this case, we'll start with the standard normal distribution. So if we look at the PDF, in this case, not every PDF is going to be like this, but if we look at the PDF for the standard normal distribution, we can see that it only depends on the square of z. Doesn't depend on like the cube of z or, you know, z raised to the first power or anything like that. And this squaring induces a symmetry to the standard normal distribution that is unique. So if we go back and look, you're going to have to squint probably to see the green line here. So this green line is the curve x multiplied by the PDF of x, where the PDF is that of the standard normal distribution. And so when x is negative, so the PDF is always positive. If you multiply it by a negative x, it's going to be below 0. If you multiply it by a positive x, it's going to be above 0. And if I ask you, okay, what's the area under the green curve, and I remind you that if the curve goes below 0, that counts as negative area. So what is like the total area of all this? 0. You can sort of see we have a symmetric shape to the green thing around 0. So we have a chunk of negative area here, a chunk of positive area here, and those are the same size. So we integrate over the whole thing, that's 0. Consequently, the expectation of a standard normal random variable is 0. That just comes from doing this integral, which is actually a little bit hard to do, but here's kind of a sketch of a proof. So we want to integrate this from negative infinity to infinity. And what the integrand is z times f, the PDF of z, integrated over z. And you can always break up an integral and add it in 2 pieces. So integrate from negative infinity to 0, and then add that to the integral from 0 to infinity. But like I said, this PDF in the standard normal case only depends on the square of z. So I can actually pull out a minus sign here and just integrate from 0 to infinity, z times f of z, whatever, and then add to it the integral from z, or from 0 to infinity of z times f of z. So we have negative something over here. That was the left piece of the green curve. And then we have positive something over here. That was the right piece of the green curve. These are equal in magnitude, so it cancels out to 0, provided these integrals converge, which in this case they do. However, there are some distributions where these integrals won't converge, in which case we say the expectation is not defined. We'll get to one of those later. They don't come up that much in practice. All right? So the expectation of a standard normal variable is 0. Furthermore, I didn't show it here, but if I integrate the function z minus 0 quantity squared, multiply that by f of z, integrated over z, I get the variance of a standard normal distribution, which happens to be 1. So whenever you hear standard be put in front of some distribution, it's basically referring to the most easily tractable mathematical case. And the most tractable mathematical case of a normal distribution is that which has a mean of 0 and a variance of 1. Consequently, the standard deviation, being the square root of 1, is also 1. So how can we go from a standard normal distribution to a general normal distribution? So let's define the new variable x, which is a function of z. And the function of z we're talking about in this case is going to be written mu plus sigma times z. And if we substitute, and so, okay, that's x is a function of z. If we wanted to write z as a function of x, it would simply be x minus mu all divided by sigma, if we just invert that relationship there. So what we can do, we're not going to go into great detail about this today, is you can substitute for z in the CDF right here. So instead of putting z, I'll put this in terms of x minus mu divided by sigma. And then I want to differentiate that with respect to x, not z. I've substituted out z. I now have x minus mu divided by sigma, where z used to be, and I'm going to differentiate this f function with respect to x rather than z. What you get in this case is a PDF for the random variable x, which is 1 divided by sigma divided by the square root of 2 pi times e raised to the power negative 1/2 x minus mu divided by sigma quantity squared. So when I differentiate the CDF with respect to x, I get an additional piece sigma in the denominator there. But pretty much I've just substituted x minus mu divided by sigma for z. And now I have the PDF for the general normal distribution. And you might have a hard time seeing it here, but the expectation of x, expectation is pretty much a linear operator. So I have the expectation of mu. Mu is not a random variable, so that's just going to be mu. And then I have sigma times the expectation of z, but I already said the expectation of z was 0. So I have sigma times 0, and I'm left with the expectation of x being equal to the mu that I specified. Similarly, if I take the expectation of the function x minus mu quantity squared, that's going to come out as sigma squared. So in general, the mean and the variance of a general normal distribution are mu and sigma squared. And it's no accident that those symbols are used for the mean and the variance of other distributions, because the normal distribution is sort of like the center of the universe for continuous random variables. So a lot of things are sort of defined with respect to the normal distribution. So that's really like the most important distribution of a continuous random variable to know. All right? Questions?
we not do the denominator for the base
Uh-huh.
this might be clear. Typically, like in problems that are fairly complex, what kind of approach do you use?
Random numbers, simulation. So, we did the bowling example. It could be done analytically, but I could also simulate 10 million frames of bowling. We can pretty much always do the simulation thing, in which case all I have to do is like summarize the mean and whatever of about 10 million random numbers. And that will give me an arbitrarily close approximation to this analytical features of the analytical posterior distribution when I can't obtain the analytical posterior distribution.
How do you incorporate the data?
The data, y and x, yeah, that's fine. But I never have to integrate with respect to y or x. I only have to integrate with respect to theta. That's still impossible, but I can work around it with the random numbers thing. We'll get to that over the course of the next few weeks. All right, here we're really just operating at a conceptual level. And one of the most important concepts to know is the normal distribution and relatedly expectations of a function of a continuous random variable, such as a normal variant. Okay, so it works for bivariate functions as well. If I have two continuous random variables, x and y, the expectation of some function g of them is going to be the double integral over the sample space of x and the sample space of y of the curve, or this is actually going to be like a three-dimensional thing here, the g function multiplied by the joint PDF of x and y, whatever that may be. And this generalizes to functions of more than two random variables. So if I have three random variables, it's going to require a three-dimensional integral. This quickly gets tedious at best, if not impossible. But conceptually, it's still an area or a hyperarea in multiple dimensions. So common examples of bivariate functions whose expectations we might be interested in. The quantity x minus the mean of x multiplied by the quantity y minus the mean of y. If x and y are continuous, the expectation of this function is still the covariance. It's just you need to do an integral to obtain it. If instead the function divides by the standard deviation of x and y, and we take the expectation of that function, we get the correlation. The correlation is still going to be between -1 and 1, still going to be unit free, still going to be a measure of linear dependence between x and y, but now x and y are continuous, so we have to do a double integral to get the value of rho. But conceptually, it's still just an area. Finally, if we define the g function as the PDF of y given theta, and we take the expectation of that g function, so we have, and we take it with respect to theta, so we multiply that g function by the PDF of theta, we get basically the expectation of this function, the PDF of y, for a given value of y, integrating over the space of theta. And this function has a lot of names. You could call it the expected likelihood of y, but it's basically just the denominator of Bayes' law. And it's obtained by integrating the numerator over theta space to purge theta. This has other names like the marginal likelihood of the data, the evidence, it's like its professional wrestling name, other things, but it's really just another expectation. It's the area of the numerator. And so if the area of the numerator is whatever it is, and you divide by that area, then the area under the curve, the PDF of theta given y and x is going to be what? Let's try that again. I got the numerator. It's some function that's a product of two functions. I figure out what the area of that is. I divide by that area. So what's the area underneath the curve on the left-hand side? 1. All PDFs have an area of 1 under them. So I'm really just dividing by whatever makes the left-hand side integrate to 1. And then it's a valid probability density function, and I can do probability stuff with it. So a lot of times we're just dividing by, or every time really, but you can just sort of think of it as, okay, the numerator, it has some area. I divide by that area. And now the thing that I'm interested in, the left-hand side, the posterior PDF, is going to have an integral of integrate to 1, and I'm ready to go. All right. So once you do that enough times, it sort of becomes second nature, even though we never really do those integrals.
We're doing that thing you said with the simulating. Sometimes at some point normalize it. So do we actually normalize the values of simulations?
No, so when we do the simulations, and again, we'll talk about this in a couple of weeks, we get draws of, let's say, theta from the conditional distribution of theta given the data. And those are consistent with this PDF that we can't get analytically. But that PDF that we can't get analytically still has an area of 1. So we don't need to do any more normalization. We just have to get draws that are consistent with the PDF that we're looking for, which is the posterior PDF. So we're going to do one graphically and analytically, and hopefully that'll sort of solidify things a little bit, but we'll get to the random number simulation part later in the course. So beta distribution. Beta distribution is perhaps appropriate for a sample space that's the 0 to 1 interval. The CDF for a beta distribution is hard to write down in a useful form. This is another one of these that it just doesn't work. But the PDF of the beta distribution is still the derivative of this function that I have a hard time writing down. But the derivative takes a relatively easy form. We have this 1 over b business, which I'll explain in a minute, multiplied by x raised to the power alpha minus 1, multiplied by the quantity 1 minus x raised to the power beta minus 1. And we often write that, so this is an equality, and then we often write this as proportional to, and then leave the terms that involve the random variable in question, in this case, x. And we omit any terms in that PDF that don't involve x, such as this b thing. So this part here to the right of the proportion sign that involves terms involving x, this is known as the kernel of the PDF. And the constant, which is not actually a constant, well, it is a constant with respect to x, but in this case, it's going to depend on the 2 parameters alpha and beta. This is just the reciprocal of the integral of the kernel. So if I take this piece here, x, well, now you can't really see it, but everything to the right of the proportionality sign, I take the integral of that. Let's call that b. I divide by b, and now I have a PDF that integrates to 1. So what is b? So if I make a function k for kernel, x, it depends on x and alpha and beta, and I just return the right-hand side over here to the right of the proportional sign, I can call the integrate function in R, which does numerical integration. It's basically that thing you already learned with like the little trapezoids, and you take the area of them and you add it all up. It's slightly smarter than that, but not a whole lot. And if you make little enough trapezoids, you get sort of arbitrarily close to the right area. That's all we need to do here. So I get my k function, and I say I want to integrate the k function from a lower bound of 0, which is the edge of the sample space, to an upper bound of 1, which is the other edge of the sample space. And I just need to provide it particular values of alpha and beta. So these are arbitrary, but they have to be positive. So I use 4/3 and 2 for no particular reason. So if I integrate the k function from 0 to 1, I get, a numerical approximation to that area, which comes out to be 0.3214286. But this is an integral that is important enough that R already has a function built in that does it. It's known as the beta function. This is the capital Greek letter beta. And if I just evaluate that at 4/3 and 2, I get an exact, or it's not even really exact, but it's the same number here. So this b, or this beta function, is just the integral of the kernel function from 0 to 1. I divide by that area. In this case, it's 0.32. And now I have a normalized, valid PDF for a random variable whose sample space is the interval from 0 to 1. And it has two arbitrary but have to be positive inputs to it, alpha and beta, that I can just choose, or I can estimate if I was doing this on real data. And we'll do that in a second. So this is just, it's like the normal, it's sort of like the normal distribution, except the normal distribution is for a random variable whose sample space is all real numbers. This is another distribution that happens to work very well and is defined for a sample space that's just the interval from 0 to 1. And it has this PDF, and this is just, this b function is just the area of the kernel function. Divide the kernel function by its area. The PDF is now going to integrate to 1. So I've got a PDF I can work with here. All right. So questions about that? No? All right. Where are my public health students at? One. All right. The rest of you sit back. Let the professionals handle this one. So this is a story based on, it's not an entirely true story, but it's a story based on actual events. In 2013, 2014, something like that, you may have heard, there was a real big outbreak of Ebola in Africa. And like the Doctors Without Borders people, sent a bunch of people to Africa to sort of try to treat the people there. And some of those doctors and nurses contracted Ebola. And then they came back to the United States. You probably saw it on CNN. They flew them to the CDC, or the hospital next to the CDC in Atlanta. And so now we have 7 people, all told, with Ebola in the United States. And so you people who are in charge of public health, wait, hands up again. All right. So you're going to have to decide if this experimental Ebola cure drug should be approved for use for people who have Ebola. So it hadn't been approved at that time. And so we're going to have 7 people who have Ebola, and they're going to get the drug. And so the quantity we're trying to get our posterior about is what's the probability that this drug is going to cure someone of Ebola. All right. This drug happens to be made by a company named MAP Pharmaceutical, biopharmaceutical, whatever. I've never heard of them either. Okay. So to start with, what are your initial beliefs about the probability that this drug will cure someone of Ebola, phrased in terms of a beta PDF? So you might, I'll flip back here, note that if alpha is equal to 1 and beta is equal to 1, we're raising things to the power of 0, and anything raised to the power of 0 is just 1. So in that case, this PDF is going to be a flat constant. So that might be what we start with if the shape parameters of this beta distribution were 1 based on our prior beliefs. So public health people, does that seem like a reasonable description of your beliefs as to the probability that this drug will cure someone, a person, of Ebola. So it's basically saying every probability of cure is equally possible. Does that seem reasonable to you? Aha! So suppose I told you in clinical trials that 21 out of 21 patients that received this drug survived. Now, what sort of shape might you put to represent your prior beliefs? That's not good. Tell me when to stop. No, all 21 subjects in the study survived in clinical trials. So, stop. All right. So let's say 4.4 and 1.7 for alpha and beta. So suppose I told you out of those 21 subjects for whom the drug at least kept them alive until the end of the study, 21 of which were monkeys. So what is your prior beliefs represented in terms of a beta PDF for the probability this drug will cure a person who has Ebola? In sort of qualitative terms. We want to keep going this way? No? Back it up? Maybe spread it out a little bit? Something like that? So suppose I told you that of the 21 out of 21 monkeys who survived to the end of the study, despite being injected with Ebola, 21 of those were injected with the cure an hour after they were injected with the disease. And, you know, and with most humans, they don't really get to the hospital within an hour of contracting Ebola. It's usually like several days later, and they might not even have a hospital in their village, and they might not have this drug. But of the 21 out of 21 monkeys who survived to the end of the study, they were injected with the cure an hour after they were injected with the disease. So now what would you say your prior beliefs are about the probability that this is going to cure a person with Ebola who contracted Ebola like a week earlier, and then they flew them into Atlanta? I mean, they got like other treatments during the time, but it was probably like, let's say, a week after they got Ebola before they would get the cure. Left or right? Left. Or something like that. So suppose I told you in another study that out of a different group of 21 monkeys that received the cure 3 days after they got injected with Ebola, 7 of the monkeys didn't make it. 14 did. Not bad for a monkey with Ebola.
How many normally did?
Huh? Like none. Well, monkeys don't usually get Ebola naturally, but for people, if you're not treated, that's not good at all. Like 98% of them or something like that. So you want, wait, we're going right? You're a public health professional now, Nigel?
No.
Okay, you don't count. The people behind you. We're going right. Let's do 3 and 2, let's say. Okay. So the trick to all this is being able to come up with a PDF that describes your beliefs before you see new data. In which case, we're actually have 7 people who got Ebola, and the Department of Ebola approved this drug for temporary usage on these people who were doctors or nurses who got Ebola. So now all you have to do is check the box that says update beliefs with new data. And you got to make it bigger. Oh, damn, it cut off. And you got to scroll right. No. Come on. Okay, here we go. Remember the stuff on the left. Okay, so what we have in the top right here is curves representing the PDF for y given, let's say, theta, where theta is the probability of a cure. So what PDF would we want to use when the outcome is either you die or you live, and there are 7 people and they're more or less independent of each other? So what's the appropriate PDF to use in that situation? Binomial. All right. So what we have in the top right there is the binomial PMF as a function of the unknown cure probability. And this is, we have different colors for different values of K, where K is the number of people who survive. So let's say we got the red curve here. This corresponds to 1% out of 7 who survive. So if the probability of a cure is, let's say, 0.4, it's unlikely that we would observe 1 survival out of 7. It's not 0 probability, but it's probably like 0.17 or something like that. So if the true probability of the cure is 0.4, you would have to be pretty unlucky to only have 1 survival out of 7. But if the cure probability is like 0.1, then 1 out of 7 is entirely reasonable for that. Anything between like 0.1 and 0.15, it's all, you know, clustered around here. If we go to this pink or purplish curve, which is 5 people survive out of 7, that is also, we're unlikely to observe that if the true cure probability is 0.4. So we would be extremely lucky to see 5 out of 7 survive if the true cure probability is 0.4. What's more likely is, you know, something around 0.7 or something. If that was the true cure probability, then seeing 5 out of 7 survive is entirely reasonable. We could do that for any value of K between 0 and 7 and see, you know, what's the probability of observing this number of survivals if the true cure probability is this or that, any number along the horizontal axis here. Now, in point of fact, 5 of the 7 doctors and nurses that got Ebola did survive. So we're going to focus on the purple curve here because this is the curve that represents the data that actually happened. Now, what frequentists will do is ignore all the stuff about monkeys. They don't count. They're monkeys. They're not part of the human population, which we're trying to make inference about. So it's like that never happened. So we're not looking at the left, we're only looking at the top right. 5 out of 7 people survived. Therefore, our estimate of the cure probability is 5/7. That's all there is. And that's indicated by the vertical line here, which corresponds to the mode of the purple curve. This is the value of the estimated cure probability such that 5 survivals out of 7 tries is the most likely data set to observe if that was the cure probability. That gets the conditionality backwards from what like normal people would think. They want to know what's the probability of a cure conditional on the data. Here, with the frequentist thing, we're saying, okay, what is the value of the cure probability such that the data we observe is the most likely data to observe, which is a real convoluted thing, but it sounds a whole lot better if you call it a maximum likelihood estimate. Because a lot of people who don't know anything about statistics, including a lot of people who know something about statistics, think when I hear maximum likelihood estimate, that's the value of theta that is most likely, which is backwards. This is the value of theta such that the data you observe is the most likely data to observe. You're like, well, that's not what I want. And frequentists are a very tricky bunch. If you look back through your statistics or your econometrics textbook, read all the footnotes in the fine print, it never tells you you should believe the cure probability is 5/7. It just says 5/7 is the value such that the most likely data set to observe is 5 survivals out of 7 tries. But suppose you have to make a decision as to whether this drug should be approved, for wide use on the basis of that. Now you have to really assess what it is you believe about the cure probability, which is what the Bayesian method of inference provides a path for you. So if we take this curve here, which represents our prior beliefs, and we multiply it by the pink curve in the top right, I didn't show it here exactly, but we get the numerator of Bayes' rule. So then we have to take the area of the numerator, divide by that area, and now we have the conditional PDF for the probability of a cure given the data. But this is going to incorporate our previous beliefs about the cure based on the monkeys and stuff, in addition to the data that we happen to observe for the 7 people who were unfortunate enough to contract Ebola while trying to help out in Africa. So that denominator of Bayes' rule, it's an area, it's the area of the numerator, that is reflected by these dash curves here in the bottom left. I could do it for any value of k that I want, but the value of k that actually happened was the pink one, and I can evaluate my beta function, and it comes out to be something a little bit less than 0.2. So if I multiply this pink curve by that pink curve, take the area of it between 0 and 1, I get some number that's about 0.2. I divide the numerator by some number that's about 0.2, and I get the posterior distribution, which is given here in the bottom right. So the solid pink curve, purple curve, is my posterior PDF of the probability of a cure given the data. But it takes into account my prior beliefs about a cure based on the monkeys and so forth. We can compare that to the dotted pink line, which I've repeated here, which was your public health colleagues' prior beliefs about the probability of a cure. And this makes sense. As we observe new data on these 7 people, the posterior PDF becomes more concentrated. We have more information, and now we're more sure, not completely sure, more sure than we used to be when we just had studies on monkeys about the efficacy of this drug. It's also, the whole thing is shifted a little bit to the right because 5 out of 7 was sort of a more optimistic result than what we thought going in, when 2/3 of monkeys survived when they got the cure like 3 days later. So it actually seems like it maybe worked a little bit better in people than it did in monkeys. But it's a small amount of data, so it could just be due to chance. So we get a PDF that's shifted to the right and squished together, representing our posterior beliefs after observing the data as to what's the probability this drug is going to cure someone, a person, with Ebola. We can compare that to the frequentist estimate, which we got here, and I replicated with the dashed line. So like I said, the maximum likelihood estimate is 5/7. And frequentist theory assures us that if we did a study over and over and over again and average the results, we would get the true answer in the population. Guess who's not going to approve a study where you give 7 people Ebola? No IRB board ever is going to approve that for your QMSS thesis. I'm sorry. We're not going to do that over and over and over again. Even if we did, who cares? If you do a study over and over again and update your posterior distribution, you're also going to get the true answer. So it's not even something unique to frequentism. I mean, the stupidity of it is unique to frequentism, but like this hypothetical thing that we could get the right answer if we did it an infinite number of times isn't. But the frequentist theory also tells us that the variance of our estimates when we do this over and over and over again is equal to p times 1 minus p divided by n, which in this case is 7. And the distribution of those estimates when we do it over and over and over again is going to be asymptotically normal. So I've drawn with the dashed line here a normal distribution whose mean is 5/7 and whose variance is 5/7 times 2/7 divided by 7, whatever that is. But you can see this normal distribution in the dashed line, it actually pokes out greater than 1. So if you take this literally, there's some probability, I don't know how much, whatever is the area to the right of 1 here, which could be evaluated by 1 minus the CDF of a normal distribution, that's telling you there's some probability that the cure probability is greater than 1, which is asinine. But the maximum likelihood estimate doesn't take into account known information, such as probabilities have to be between 0 and 1. Nor does it take into account known information about when we did this study on monkeys. But the frequentist view is sort of very black and white. Either you say monkeys are equivalent to people, and instead of having an n of 7, you have an n of 7 plus 42, because there were 42 studied on monkeys. Or you say monkeys, people, different species. Nothing about the monkeys counts. But the reason why we do drug tests on monkeys is because in like a lot of other situations, we found that it tends to work similarly between monkeys and people. And like genetically, they have an immune system that's like 99% similar to us. So, there's reason to believe this is going to be some information. But honestly, if you talk to the CEO of MAP Pharmaceutical, he was not super confident that this was going to work on people. He had reason to maybe have a PDF like this, but he didn't know it was going to work on people. Turns out it did. Turns out they can only make like 1 dose per month. So some other drug companies kind of develop some other drugs that are easier to mass produce and have sort of overtaken them. But if you were, say Pfizer didn't make an Ebola drug or whatever, you just had this, are you going to invest, you decide to invest in that company on the basis of this posterior PDF on the cure probability? Because this company is going to need like $1 billion to get the drug to market. If you're the US government, are you going to want to approve this for widespread use? Are you going to take whatever stockpile you have, give it to an African country on the basis of this probability? Are you going to continue to subsidize the development of this drug if, this is how successful it is? All these questions involve like billions of dollars. And so you really need to make sure you know what your posterior beliefs about the success of this drug are, conditional on the data you have. Monkeys, people, like the theory of it, which I don't know, but presumably some, public health person does. Got to figure out all this stuff. before you can make decisions about it. Question? Yeah, we'll get to hierarchical models much later. It gets weird for frequentist.
What's the y units on that bottom right figure?
I didn't put them in, but they're units of PDF. So they're pretty much arbitrary, except all the solid curve here, it integrates to 1. So it's units of PDF, and we'll do it on the next slide. Yes, Joe.
Will make sure you use the language and maximum likelihood off of that or posterior distribution?
No. Maximum likelihood is frequentist.
So how would what's the best way to communicate that? Once you've generated that posterior distribution, here with the frequency.
Right. Well, go away. But if I were advising, the secretary of Ebola, I could say, the expectation of my beliefs, I can use this PDF to derive that expectation. I can tell you the posterior median. There's a 50% chance the probability of a cure is less than this, and a 50% chance it's greater than that. Things like that to make the decision on how to proceed in light of this. We've got a lot of fingers. Public health people are giving us a decision.
No, I was going to ask, so you said you multiply the two curves, the top one will not be.
That gives you the numerator. Then I've got to divide by this constant in the bottom left to get the denominator. And the solid curve over here is the left-hand side of Bayes' rule. All right, let's do this analytically. It's one of the few cases where we can. Okay, so each case is Bernoulli. We observe 7 of them, so they're collectively binomial. So before you see the results, the PMF for K successes out of 7 trials is the binomial PMF we learned last time. In what we actually observed was 5 out of 7 people were cured. What are your beliefs about P? So the posterior distribution of P, conditional on alpha, beta, and K, and n equals 7, but I didn't write that part. So we've got the numerator of Bayes' law here with our prior PDF on P, our likelihood or our binomial PMF for K, and then divide by whatever the area in the numerator is. So we can write that, again, dropping constants, which don't depend on P. We're left with the proportion thing. This first part here, which you can't see if I highlight it, but the 2 terms to the left here come from the beta PDF. So P raised to the power alpha minus 1, 1 minus P raised to the power beta minus 1. And then these last 2 terms here come from the binomial PMF for K, which is P raised to the power of K times 1 minus P raised to the power 7 minus K, in this case, because I had 7 people in my study. So that implies by the rule of exponents. So if you have like A raised to the power of B and C raised to the power of, no, if you have A raised to the power of B and whatever, you have 2 things that are the same base and you raise them to different exponents and multiply that together, you can sum the exponents. Trust me, even though I can't say it. So what we're left with is P raised to the power alpha plus K minus 1 times 1 minus P raised to the power beta plus 7 minus K minus 1. And we can rewrite that as P raised to the alpha star minus 1 times 1 minus P raised to the power beta star minus 1, where alpha star is equal to alpha plus K and beta star is equal to beta plus 7 minus K. And K turned out to be 5. So this right here, this kernel is the same as the kernel of a beta distribution. And consequently, if we want to divide that by the area underneath that kernel, all we have to do is evaluate the beta function that's already built into R at alpha star and beta star. So in this case, the posterior distribution is in the same family as the prior distribution. This is what's known as a conjugate relationship between the prior on P and the PMF for K. So when conditioning on the data doesn't change the family of the distribution, it stays beta, but all it does is shifts over the parameters of the distribution from alpha to alpha star and beta to beta star. That's called conjugacy. And this is the case that Thomas Bayes, not with Ebola, but with the beta distribution, figured out in like 1760 something. So it started with this. And, you know, we can divide by the area, and now we have the normalized PDF for the beta posterior that's given by the solid pink curve here. So that's how I got the solid pink curve. You guys told me the alpha and the beta, and then I just shifted alpha by K and shifted beta by 7 minus K. Okay, so there was a question up here. Now what do I do with it now that I have a posterior distribution that describes my beliefs about the probability of a cure given the data I've observed, whether it's monkeys and people all together? So what you can do is you can take the expectation of that random variable of your posterior beliefs. Turns out for a beta distribution, the expectation is equal to alpha star divided by alpha star plus beta star. If you do the integral, it's on Wikipedia. That's the expression for the expectation of a beta random variable that has shape parameters alpha star and beta star. I could also take the posterior median of my beliefs about the probability of a cure. That's harder to, it's impossible really to write down analytically, but you could compute this in R using the Q beta function. Evaluated at 0.5, this is going to tell you a median, but you need to supply it the alpha star and beta star, which are your updated parameters after conditioning on the data. Moreover, you could calculate the probability that the cure probability is good enough to move forward. So let's say you say, okay, if the probability of a cure is 0.6, that's good enough for us to approve it for wide use or like make more of it or some important decision like that. To do that, you just have to evaluate 1 minus the CDF of a beta distribution with parameters alpha star and beta star. That can be done using the P beta function. But if you want the area to the right as opposed to the area to the left, you need to specify lower equal false. And so if I go back here, I didn't calculate this, but let's say 0.6 is good enough. So how much area is to the right of 0.6 under the solid pink curve? I don't know. But if that's high enough for you as the decision maker, and 0.6 is like your threshold for, you know, then you can say, okay, there's a, I don't know, maybe 70% chance that this is good enough. And maybe we can go with that from there. So do I have any more stuff? What you don't do is say the most likely value of the parameter, the cure probability is like 0.68. Because that's not good enough for making the decision. Yes, the most likely value is 0.68, but it's unlikely to be 0.68. There's a lot of other area to the left and to the right here. So that's insufficient for making any sort of important decision. You need a whole posterior distribution or some summary of a whole posterior distribution, like a mean or a median. You can do the variance, whatever. It's got to be a function of the whole posterior distribution, because the whole posterior distribution tells you information about your beliefs about this cure probability. Okay, we're out of time. I didn't get to my last slide on prediction, but we'll be sure to pick that up next week probably. There's some reading on the syllabus for Tuesday. Go away. That you should read, particularly if you're not previously familiar with matrix algebra and like vector multiplication and stuff. I will post a homework late tonight. There'll be a session, 2 sessions actually tomorrow with Imad in room 270B of IAB if you haven't done our markdown before. Imad's not going to go over he's not going to review anything. He's just going to tell you how to work with the R markdown format, which is what you need to do to turn in your homework. But if you've taken a class with me before, or you know the R markdown format, you don't need to show up. And if you can't show up, we're going to try to video it, and so you can watch it later. All right? That's it.
Just one question about.
Hold on one second. Stop broadcast.